What's up, bitches? Today we're going to learn cogenerative Rankine cycle. I'm not going to draw the entire process with the boilers because you don't need to know that. What you do need to know is a TS diagram. So we start over here at point 1, goes straight up, ideally point 2. Then it's going to touch the saturation lines over here at point 3. Then there's a point 4 over here in the middle of these two shits. Goes up over here at point 5. Then goes into your turbine, leaves the turbine. Then there's a straight line over here. 7. Sometimes point 7 is within the curved lines, by the way. And then finally point 8. That's it. It's super easy. So keep in mind, wherever you see curved lines, there's heat being involved. And wherever you see straight vertical lines, there's work being involved. So over here is work in, and over here work out. This kind of looks, the cogenerative Rankine cycle kind of looks like your closed feed water systems, where like a portion of your water, a fraction, which is Y, goes into the cogenerative heater thing, and the rest just follows the normal thing, and that's it. This part over here, 0.3 to 0.7 to 0.3, it's Q process. This is different than the like Q in and Q out. It's just like more internal. That's why. What you do have to know for this type of Rankine cycle is that W work is equal to the specific volume times delta P. You're gonna have to use this equation to solve a lot of your problems. Next, you have to know that the work and Q's, you calculate them using delta H. So every problem that you start, you have to find all of the H's at all 8 of these points. Lastly, you have to know that for these types of Rankine cycles, you don't use the thermal efficiency. You use something else called I think the utilization factor, some shit like that. It's equals to W net plus Q process divided by Q in. Just one little extra step, and that's it. Super easy. Also, one last thing before, because I always forget this. Wherever you see Q in and Q whatever being involved, it's always constant pressure. CP, constant pressure, okay? So whenever they say, oh, the turbine inlet is at, I don't know, 1 MPa, know that over here is like this entire part over here is at 1 MPa, okay? Constant pressure, and that's it. All right, now let's do an example just so we understand better. I highlighted whatever is important. It's just giving us a bunch of information for a cogeneration plant. What you have to do is you have to read your question very carefully, see what they're asking. Over here, they're asking the utilization factor. Once you understand what's happening, the first step that you do is you draw the TS diagram. This is going to help you to not get lost and not make stupid mistakes. So I'm just going to write the TS diagram for the cogeneration plant. All right, we have everything. Since there's no turbine efficiency, whatever, these are all straight lines. Okay, we know over here is constant pressure, constant pressure, constant pressure. Q out, over here Q in. This part over here is Q process. Work in over here, work in over here, over here, work out. Wherever you see vertical lines, it's work out. Next, you're going to want to draw a table for yourself just so it's easier to keep track of all the enthalpies. Next, we start reading the question, okay? It's saying that steam enters the turbine. Turbine is over here at 0.6 at 7 MPa and 500 degrees Celsius. Since over here is constant pressure, we also have P5 to be 7 MPa. It's just that the temperature changes. And you could see over here that there's a temperature difference. 1/4 is extracted from the steam. So over here, Y is equal to 0.25 from the turbine at 600 kPa. So 0.7 is 0.6 MPa. Since it's constant pressure over here, all of this part over here is constant pressure. So 0.6, 0.6, 0.6. And then the remaining of the steam continues to 10 kPa. So over here at the bottom, 0.1, it's 10 kPa. All right. Then it's giving us the mass flow rate, the steam through the boiler is 30 kilograms per second. The boiler is up over here. It's saying that all of the the total mass basically is equal to 30 kilograms per second. All right. Now to find the utilization factor, we have to find the enthalpies, the H's, for all of these points, okay? So let's start. At point 1, we could see it's on the saturation lines, and we have the pressure. So all you have to do is check the table. Since it's on the left saturation lines, we know that it's a fluid. So HF at 10 kPa. Looking at the water tables, we see that it's equal to 191.81. So here we can write H1 equals 191.81. Next, to find point 2, we just have the pressure, but it's not saturated. So what do? You have to keep in mind that wherever you see a vertical line, there's work being involved. So you have to use this equation. Work equals the specific volume times the pressure difference. To find the specific volume, again, it's saturated. Point 1 is just saturated water. So you just check the saturated fluid specific volume, which is equal to 0.00101. So work is equal to 0.00101 times the pressure difference in kilopascals, okay? P2 is 0.6 megapascals, so 600 kilopascals, negative 10. Calculating this, you get a work of about 0.5959. You also know that the work is equal to the enthalpy difference. And we have H1, so H2 is equal to W, 0.5959, plus H1, 191.81, giving us our H2 to be 192.41. So H2 equals 192.41. Next, for point 3, we see that it's on the saturation lines again. And over here, P3, oh, we have the pressure. So again, all you have to do is check the enthalpy for saturated fluid at this point. H3 over there, looking at the tables, is equal to 670.38. All right. Now, looking at point 4, we have point 4. You see, we only have the pressure, but we don't have the temperature, and it's not saturated. So it's a little bit harder. What do you do? You have to take into consideration that at point 2 and point 3, they combine into point 4 over here, okay? What this means is that using the E in equals E out formula, M2 times H2 plus M3 times H3 equals M4 times H4. Okay? Keep in mind that over here, like beyond 0.7, some of the water like leaves the proper path and goes into the cogeneration like heater. So M2 is equal to the total mass flow rate, and it's 75% of it because the other 25 is at 0.3. So times 0.75 times H2, which we found to be 192.41, plus total mass flow rate times the other 25% times H3, which we found to be 670.38, is equal to the total mass flow rate, 0.4, which is just a combination of both. So I'm just going to keep it M. You don't need to multiply it by anything else, times H4. Replacing M dot to be 30 kilograms per second, as told by the problem statement, you can finally find H4 to be about 311.9. So you're going to write that in your table as well. H4 equals 311.9. That's it. Very easy. You just have to know this part by heart for your cogeneration cycles. Next, at point 5, you have to do the same thing as what you did for point 1 and point 2, okay? we have to find the specific volume at 0.4. What you basically have to do is checking the tables. It's a little harder to interpolate or anything. So you're going to approximate by looking at your tables, and it's equal to 0.01026. When you write this in your exam, make sure that you write approximate. Otherwise, your professor's going to think you're retarded. Just write this and say, oh, you're approximating using H at 311.9. Okay? Basically, just check at the tables and you'll realize that the specific volume, there's a very, very slight difference. So it's not that big of a deal if you approximate using these values. Check whatever is closest to 311.9. You don't really need to interpolate anything. And you just use that specific volume, okay? So, W is equal to specific volume times delta P. Equals to 001026. It's already a super low number, so it doesn't matter. Times the pressure difference from 0.5 to 0.4. 0.5 is 7,000 kilopascals. 0.4 is 600. So, times 7,000 negative 600. Work is about 6.5664. Had we chosen an any smaller value, it's barely going to make a difference to this, so it doesn't matter. Next, we know that work is equal to H5 negative H4. So H5 is equal to 6.5664 plus H4, which we found to be 311.9, giving us an H5 of about 318.47. That's it. Super easy. Next. To find 0.6, you have the pressure and the temperature. So you just have to check your superheated tables to find H6 to be about where is it in the table over here? 3411.4. Now, observing this, since you could see that 7 and 8.678, they're like perfectly vertical, meaning yeah, there's work being let out, but like there's work being done by the system, but also the enthalpy is the same, S is the same. So at 0.6, you need S6, which is equal to about, where did I write it? 6.8 in the tables over here. Now we could begin finding 0.7. 0.7, actually first let me clean this up real quick. 0.7, we have a pressure of 0.6 megapascals and an entropy of about 6.8. Reading the superheated tables, you're going to see that you basically have to interpolate, just like all your other cycle problems, okay? So reading the table, well, this is the equation. H is equal to H1 plus the slope times the S that we have, negative S1. Reading your tables and plugging in all the numbers, you're going to get an H7 of about 2774.58. All right. H7 equals 2774.58. You're going to do the exact same thing for 0.8. However, you're going to see that 0.8, it's within the curved lines. That means there's a quality to it. It's not superheated. Even if you do check the superheated tables, you're going to realize that, oh yeah, it's not superheated. The value is not there. So you check the pressure. The pressure P8 is at 10 kilopascals. And you have the S to be 6.8. So you just have to find the quality, which is equal to S negative SF divided by SFG. This is an equation that you have to know by heart. So reading the tables, we get the SF of about 0.6492 and SFG to be 7.4996. Therefore, our quality is about 0.82. So now we can find H, which is equal to HF plus X HFG. Reading the tables again and plugging in the values, you're going to get an H8 of about 2154.69. Nice. H8 equals 2154.69. And that's it. We have all of the enthalpies. Now we're ready to calculate the utilization factors. Let me just clean this up real quick again. All right. So utilization factor is equal to W net plus Q process divided by Q in. All right. So to find W net, you need to find W in and W out. In at both of these points over here. I'm gonna label this as 1 plus W in at the second pump. So we basically calculated these before, which I erased, but I wrote it down on a piece of paper. It was basically 0.5959 times. You're gonna have to use the mass flow rate this time. It's over here at this point. It's equal to 1 minus y. It's 75% of it. The other 25% it's up here. The 75% of the water is down here. So 0.75 times the total mass flow rate, which was 30. Plus the second work done by the pump over here, which we calculated before. I just erased it. It's equal to 6.5664. Next over here, 0.2 and 0.3, all of the water is being combined at 0.4. So beyond 0.4, this entire part over here, it's 100% of the, you're considering it to be 100% of the water. So it's just equal to 30. Calculating this, the total work being done on the system is equal to 210.4 kilowatts. All right, next. The work being done by the system is over here, 0.6, 7, and 8. So, work out is equal to the total mass flow rate at H6 negative H7 plus whatever's down over here. Now keep in mind that you can't just multiply this by m dot because it's not 100% of the water. 25% leaves over here, so the other 75% is over here. So times 0.75 times m dot, which m dot is equal to 30. Plugging in all the values, I'm not gonna copy down everything over here, but you're gonna get a W out of about 33,074.63 kilowatts. So work net is equal to work in negative work out. Sorry, it's equal to work out negative work in, which is equal to about 32,864.225. All right, next for Q in, it's up over here, and since from 0.456 all the way to 7, you're considering it to be 100% of the water. So we're just gonna take m dot Q in is equal to 30 times, which one was it? H6 negative H5 equal 30 times H6 was 3411 negative H5, which was 318.47. Right? Yeah. Calculating this, you'll get a heat in of about 92,787.9 kilowatts. And that's it. We have everything to find the utilize. Actually, no, not yet. You need the Q process. Q process is heat being done by the co-regenerative process, which is right over here, okay? So here we see that it's 25% of the water. So 0.25 times 30. And it's 0.7 to 0.3. Equals 0.25 times 30 times H7 negative H3. H7 is 2774. Negative H3 is 670.38. Right? Yeah. Oh, this is 5, sorry. Right? No, it's good, it's good. Okay, so Q process, solving for, like, calculating this, you should get a Q process of about 15,781.5 kilowatts. Okay, now we have everything to calculate the utilization factor. W net negative plus QP divided by Q in. W net is up here, 32,864.225 plus Q process 15,781.5 divided by Q in, which is this one, 92,787.9, giving us a utilization factor of about 52.4%. This is basically your thermal efficiency for the cogenerative Rankine cycle. And that's it. That's how you solve a cogenerative Rankine cycle problem.